Hi, DocRevis here with Watch Me Work It. Determine the hybridization of atoms in a Lewis structure. Watch me work it. First, some guidelines to use. First thing you want to do is count the total number of atoms plus lone pairs around the atom, while ignoring the bond multiplicity. Whether it's double or triple bond, doesn't matter. You simply want to know how many objects are attached to the central atom. And remember not to count the central atom. Next, assign superscripts to SPDF orbital locations that equal the total around the atoms based on the maximum subscript of S. You can add 1, P 3 because they're 3 degenerate levels, D 5 because they're 5 degenerate levels, and F 7. So essentially, these are going to be geometrical locations to place the atoms and lone pairs around the central atom in. Got it? By the way, the SPDF sum also equals a B plus E total when you're doing the ABE or AXE format. So if you have your ABX format, ABE format, and you sum those up, that's the number you're looking for to be around it. All right, so let's do some problems. Here we go. Let's start here with the hybridization of carbon dioxide. The hybridization of carbon dioxide, you can either draw out the full Lewis structure to take a look at it. If you intuitively just simply know what it is, you can go to work. In this case, we know that carbon dioxide looks like this. But actually, without even drawing it, I know that there are no lone pairs on carbon. Okay? The best Lewis structures don't put lone pairs on carbon in Gen Chem. Okay? So really, I just have what? 2 objects around the central atom here. And so I'm going to locate one of them in the S, and I'm going to put the other one in the P, and we don't like to write 1, so this is going to be an SP hybridized. That's it. Count it and load the orbitals. Got it? So the next one's going to be BH3. BH3 does not have lone pair. There are no lone pairs around boron. Therefore, I can simply go to work and call this S. I have 3 groups to load. That's 1. P, I'll need to put 2 of them in there, and that's going to be SP2 because there are 3 total groups. This number here will equal this number here. Get it? Okay. If this were the ABX format or ABE format, this would be AB3. 3 adds up to these numbers at the top. The next one, silicon. There's also no lone pairs on silicon here, but I'll just draw out the little structure just so you can see it. And so I'm just going to use the bars here and the bromide here, just shorthanding it here. So key feature here is the hybridization. So hybridization here is SP3 because I have 1, 2, 3, 4 groups around silicon. Doesn't matter how crowded it is. I only care about the silicon. I don't care how messy it is out here. I only care about the silicon. And there's 1 there, and there's 3 others. So I need to feel that equals 4. So we don't write the 1s again. So it's SP3. Next, let's take a look at some others here. Here we have carbon again. Carbon, no lone pairs. I know that. Therefore, I'm going to do it. SP3 because there are 4 groups. Nitrogen, NH3, but what I know is that nitrogen has a lone pair on it. Nitrogen has a lone pair on it because it's located in group 15. Okay? And I know that. So here we have that. So I have 4 objects around it. This also is SP3. Water, this is H2O. I know the Lewis structure of water. And oxygen is located in group 16 with 2 things around it, meaning it has 2 lone pair. This is also SP3. So note here, SP3 for methane with no lone pairs, SP3 for ammonia with 1 lone pair, and SP3 for water with 2 lone pair. The ABE format for this is AB4. This is AB3E, and this is AB2E2. Get it? So you can have the same parent hybridization for different geometries. Okay? Let's do this one. Here we have SO3. The best Lewis structure for this looks like this, or at least one reasonable Lewis structure looks like this, with an expanded octet. And if we look around this, we see that this is going to be a SP2 because there's 1 plus 2 equals 3 objects around it, SP2. If I do NEBR2, then this is going to be NE with a BR and a BR. I'm going to fill in these lone pairs just for kicks and grins, but I don't really need them to answer this. I'm only doing this to show you that it doesn't matter about the lone pairs on these. And what is it? SB here. So this I only need to put 2, 2, 4, 6, 8. There we go. Yep. So we have all the electrons assigned here. And so this is going to be a S for one of the atoms, and it's going to be a P because we need 1, 2. We have 3 lone pairs and 2 bromines for 5. It's going to be a 3. That's 3, 4, 5 D 1 for SP3D. Boy, I worked through that one, didn't I? Okay, so SP3D adds up to 5 objects around it, 3 lone pair, and 2 atoms, 2 bonded groups. The ABE format for this is AB2E3. And then we have XE with 6 hydrogens on it. I'm just drawing them out here to get a tally on it. And so 2, 4, 6, 2, 4, 6, 8, 10. Let's see here. So we need to make sure we have all the electrons accounted for. Oh, I didn't draw 6, did I? 1, 2, 5. There we go. Nice. So we have 6 around this. Okay. And so that means 2, 4, 6, and it means we're short 1 lone pair for the final Lewis structure. And so that means we have 6 objects, 6 bonded groups, and 1 lone pair for 7. So that's going to be SP3D 3, 4, 5, 6, 7. That's 7. There we go for that. So this is going to be finally SP3D3. Okay, so that's how you do the hybridization. You simply count the object around it and assign it to SPDF. So note the number it maxes out, S1, P3, D5, F7. So that's how you do it. Watch me work it.